In probability theory and statistics, the binomial distribution is the discrete probability distribution of the number of successes in a sequence of n independent yes-no experiments, each of which yields success with probability p. Therewith the probability of an event is defined by its binomial distribution. A success-failure experiment is also called a Bernoulli experiment or Bernoulli trial. When n equals 1, the binomial distribution is a Bernoulli distribution. The binomial distribution is the basis for the popular binomial test of statistical significance. The binomial distribution is frequently used to model the number of successes in a sample of size n drawn with replacement from a population of size n. If the sampling is carried out without replacement, the draws are not independent and so the resulting distribution is a hypergeometric distribution, not a binomial one. However, for n much larger than n, the binomial distribution is a good approximation, and widely used. Specification, probability mass function. In general, if the random variable x follows the binomial distribution with parameters n and p, we write za b, n, a p. The probability of getting exactly k successes in n trials is given by the probability mass function. For chi equals a0, a1, a2, an, where is the binomial coefficient, hence the name of the distribution. The formula can be understood as follows: we want k successes and na aak filures na aak. However, the k successes can occur anywhere among the n trials, and there are different ways of distributing k successes in a sequence of n trials. In creating reference tables for binomial distribution probability, usually the table is filled in up to n/2 values. This is because for k n/2, the probability can be calculated by its complement as. Looking at the expression e, k, an, ap, as a function of k, there is a k value that maximizes it. This k value can be found by calculating and comparing it to 1. There is always an integer m that satisfies. E, k, an, ap, is monotone increasing for Km and monotone decreasing for Km, with the exception of the case Wherep is an integer. In this case, there are two values for which E is maximal, P and PA1. M is the most probable outcome of the Bernoulli trials and is called the mode. Note that the probability of it occurring can be fairly small. Recurrence relation. Cumulative distribution function. The cumulative distribution function can be expressed as: where is the floor under k, that is the greatest integer less than or equal to k. It can also be represented in terms of the regularized incomplete beta function, as follows. Some closed-form bounds for the cumulative distribution function are given below. Example: suppose a biased coin comes up heads with probability 0.3 when tossed. What is the probability of achieving 0, 1? 6 heads after 6 tosses? Mean and variance, if x to be n, p, that is, x is a binomially distributed random variable, n being the total number of experiments and p the probability of each experiment yielding a successful result, then the expected value of x is. For example, if n equals 100, and p equals 25 over 100, then 25% of the results are likely to be successful. It is expected that 25 results are successful even though it is not certain. And the variance. Mode and median, usually the mode of a binomial b, n, a euro p, distribution is equal to, where is the floor function? However Whenp is an integer and p is neither 0 nor 1, then the distribution has two modes, p and PA1. When p is equal to 0 or 1, the mode will be 0 and n correspondingly. These cases can be summarized as follows. In general, there is no single formula to find the median for a binomial distribution, and it may even be non-unique. However, several special results have been established. If np is an integer, then the mean, median, and mode coincide and equal np. Any median m must lie within the interval Alschnapor per mil ma per mil or npaoe per mil. A median m cannot lie too far away from the mean, manp per mil currency min a euro ln2, max p, 1 APA euro. The median is unique and equal to mi equals around, NP, in cases when either PA per mil 1 currency are ln2 or PA per mil yen ln2 or ma AAN PAA per mil min P, A1 AAAP. When pa equals A1 half and n is odd, any number m in the interval are 1 half, na AA1, AA per mil ma per mil 1 half, na plus A1, is a median of the binomial distribution. If pa equals A1 half and n is even, then ma equals AN/2 is the unique median. Covariance between two binomials: if two binomially distributed random variables x and y are observed together, estimating their covariance can be useful. Using the definition of covariance, in the case now equals A1 we have: the first term is non-zero only when both x and y are 1, and I1/4 x and I1/4 y are equal to the two probabilities. Defining PB as the probability of both happening at the same time, this gives. And for n independent pairwise trials, if x and y are the same variable, this reduces to the variance formula given above. Related distributions: sums of binomials, if ZA b, n, AP, and YA b, m, AP, are independent binomial variables with the same probability p, then ZA plus a y is again a binomial variable. Its distribution is conditional binomials, if ZA b, n, AP, and, conditional on x, YA b, x, AQ, then y is a simple binomial variable with distribution. For example, imagine throwing n balls to a basket ux and taking the balls that hit and throwing them to another basket uy. If p is the probability to hit ux, then ZA b, n, AP, is the number of balls that hit ux. If q is the probability to hit uy, then the number of balls that hit uy is YA b, x, AQ, and therefore YA b, n, a PQ. Bernoulli distribution: the Bernoulli distribution is a special case of the binomial distribution, where now equals A1. Symbolically, ZA b, 1, AP, has the same meaning as ZA Bern, P. Conversely, any binomial distribution, B, n, AP, is the distribution of the sum of n Bernoulli trials, Bern, P, each with the same probability P. Poisson binomial distribution: the binomial distribution is a special case of the Poisson binomial distribution, which is a sum of n independent non-identical Bernoulli trials Bern, pi. If x has the Poisson binomial distribution with P1 equals AA euro equals FNA equals P, then ZA b, n, AP. Normal approximation: if n is large enough, then the skew of the distribution is not too great. In this case, a reasonable approximation to be, n, AP, is given by the normal distribution. And this basic approximation can be improved in a simple way by using a suitable continuity correction. The basic approximation generally improves as n increases and is better when p is not near to 0 or 1. Various rules of thumb may be used to decide whether n is large enough, and p is far enough from the extremes of 0 or 1. One rule is that both x equals np and n, 1 AAAP, must be greater than a 5. However, the specific number varies from source to source, and depends on how good an approximation one wants. Some sources give 10, which gives virtually the same results as the following rule for large n until n is very large. A second rule is that for n greater than 5 the normal approximation is adequate if. Another commonly used rule holds that the normal approximation is appropriate only if everything within 3 standard deviations of its mean is within the range of possible values, that is if. The following is an example of applying a continuity correction. Suppose one wishes to calculate PR, ZA per mil 8, for a binomial random variable x. If y has a distribution given by the normal approximation, then PR, ZA per mil 8, is approximated by PR, YA per mil 8.5. The addition of 0.5 is the continuity correction. The uncorrected normal approximation gives considerably less accurate results. This approximation, known as de Moivre-Laplace theorem, is a huge time saver when undertaking calculations by hand. Historically, it was the first use of the normal distribution, introduced in Abraham de Moivre's book The Doctrine of Chances in 1738. Nowadays, it can be seen as a consequence of the central limit theorem since B, n, AP, is a sum of n independent, identically distributed Bernoulli variables with parameter a p. This fact is the basis of a hypothesis test, a proportion Z test, for the value of p using xn, the sample proportion and estimator of p, in a common test statistic. For example, suppose one randomly samples n people out of a large population and asks them whether they agree with a certain statement. The proportion of people who agree will of course depend on the sample. If groups of n people were sampled repeatedly and truly randomly, the proportions would follow an approximate normal distribution with mean equal to the true proportion p of agreement in the population and with standard deviation I Florina equals a, p, 1 AAAP, 2. Large sample sizes n are good because the standard deviation, as a proportion of the expected value, gets smaller, which allows a more precise estimate of the unknown parameter a p. Poisson approximation, the binomial distribution converges towards the Poisson distribution as the number of trials goes to infinity while the product np remains fixed. Therefore the Poisson distribution with parameter I equals np can be used as an approximation to b, n, p, of the binomial distribution if n is sufficiently large and p is sufficiently small. According to two rules of thumb, this approximation is good if NA per mil beta 20 and PA per mil 0.05, or if NA per mil beta 100 and NPA per mil 10. Limiting distributions, Poisson limit theorem, as n approaches a and p approaches 0 while np remains fixed at IAA 0 or at least np approaches IAA 0, then the binomial, n, AP, distribution approaches the Poisson distribution with expected value I, de Moivre Laplace theorem, as n approaches a while p remains fixed, the distribution of approaches the normal distribution with expected value 0 and variance 1. This result is sometimes loosely stated by saying that the distribution of x is asymptotically normal with expected value np and variance np, 1 AAAP. This result is a specific case of the central limit theorem. Beta distributions provide a family of conjugate prior probability distributions for binomial distributions in Bayesian inference. The domain of the beta distribution can be viewed as a probability, and in fact the beta distribution is often used to describe the distribution of a probability value p. Confidence intervals. Even for quite large values of n, the actual distribution of the mean is significantly normal. Because of this problem several methods to estimate confidence intervals have been proposed. Let n1 be the number of successes out of n, the total number of trials, and let be the proportion of successes. Let xi plus or minus /2 be the 100, 1 ai plus or minus /2, th percentile of the standard normal distribution. Wald method. A continuity correction of 0.5/n may be added. Agresti-Cool method. Here the estimate of p is modified to arcsine method. Wilson method. The exact method is the most conservative. The Wald method, although commonly recommended in the textbooks, is the most biased. Generating binomial random variates, methods for random number generation where the marginal distribution is a binomial distribution are well established. One way to generate random samples from a binomial distribution is to use an inversion algorithm. To do so, one must calculate the probability that p, x equals k, for all values k from 0 through n. Then by using a linear congruential generator to generate samples uniform between 0 and 1, one can transform the calculated samples u, 0, 1, into discrete numbers by using the probabilities calculated in step 1. Bounds for the cumulative distribution function, for Ka per mil currency np, upper bounds for the lower tail of the distribution function can be derived. In particular, Hoeffding's inequality yields the bound, and Cherenov's inequality can be used to derive the bound. Moreover, these bounds are reasonably tight when p equals 1/2, since the following expression holds for all Ka per mil 3 nn/8. However, the bounds do not work well for extreme values of p. In particular, as p1, value f, k, n, p, goes to 0 while the upper bound above goes to a positive constant. In this case a better bound is given by where d, ap, is the relative entropy between a coin and an p coin and Bernoulli, p, distribution. Asymptotically, this bound is reasonably tight. See for details. An equivalent formulation of the bound is: both these bounds are derived by directly minimizing the Cherenkov bound without any approximation in. See also logistic regression, multinomial distribution, negative binomial distribution, references, Wadsworth, G.P. Introduction to Probability and Random Variables. USA, McGraw-Hill, New York. PA 52 Hamilton Institute. The Binomial Distribution, October 20, 2010. Newman, P. Albert Median der Binomial und Poisson-Verteilung. Wissenschaftliche Zeitschrift der Technischen Universität Dresden 19, 29 €33, Lord, Nick. Binomial averages when the mean is an integer, The Mathematical Gazette 94, 331-332. A. B. Cars, R. Booman, J. M. Mean, median and mode in binomial distributions. Statistica Neerlandica 34, 13 €18 doi, 10.1111 per joule 1467-9574.1980 TB00681XA, A. B. Hamtzer, K. The smallest uniform upper bound on the distance between the mean and the median of the binomial and Poisson distributions. Statistics and Probability Letters 23, 21 €25 doi, 10.1016/0167-7152, 94, 00090 UA, A. B. Box, Hunter and Hunter. Statistics for Experimenters. Wiley. PA 130, NIST Semitech, 7.2.4. Does the proportion of defectives meet requirements? E-Handbook of Statistical Methods. AB NIST Semitech, 6.3.3.1. Counts Controlled Charts, E-Handbook of Statistical Methods. Mackay, David. Information Theory, Inference and Learning Algorithms. Cambridge University Press. First edition. ISBN A978-0521642989A, A. B. Brown L.D., Kai T. and Das Gute A. Interval Estimation for a Binomial Proportion. Statists I16, 101 €133, Agrestia, Cool BA. Approximate is better than exact for interval estimation of binomial proportions. The American Statistician 52 119 €126, Piers M.A. Confidence Intervals for a Binomial Proportion, Comparison of Methods and Software Evaluation. Wilson E. B. Probable Inference, The Law of Succession, and Statistical Inference. Journal of the American Statistical Association 22, 209 €212, DeRoy, Luke. Non-Uniform Random Variate Generation, New York, Springer Verlag. Kashitwik Langukal, B. Schmeiser, B. W. Binomial Random Variate Generation. Communications of the ACM 31, 216 €222 doi, 10.1145/42372.42381. Matoa Ek, J., Vondrak, J., The Probabilistic Method, 1. ABC Arasha and L. Gordon, Tutorial on Large Deviations for the Binomial Distribution, Bulletin of Mathematical Biology 51, 1, 125 €131, 2. External links, Interactive Graphic, Univariate Distribution Relationships, Binomial Distribution Calculator.